Hello, everyone. I'm Jonathan Perlett, and today we're going to discuss some more advanced topics in C. So what we're going to talk about today is pass by reference versus pass by value semantics, how arguments are handled for functions. We're going to talk about how you can modify arguments to a function. We're going to talk about why we use pointers to structs as opposed to passing around structs between functions themselves. We're going to talk about how we can return pointers to make things like constructor functions or generators of lists or things like that. We're going to talk about how strings are represented in C and how we can work with them. And we're going to talk about 2D arrays, pointers to pointers. So let's begin with pass by value semantics. So normally in C, when you pass variables to arguments, or when you pass variable arguments to a function, they're copied into variables in the function's local scope. Anything done inside the function cannot affect the original variable. The classical example of this can be seen here. So let's just copy paste this into our IDE and go over it a bit more in depth. So what I mean when I say when you're passing variables as arguments to functions, we have this integer I and we're passing it to the function boring. What boring does is take its argument and increment it by 5, and then it prints the value of that argument. We are first going to print the value of I before we call the function with it as the variable, or with it as the argument, and after. So let's go ahead and run this. So we can see before the function call here, the value of I is 6. Inside the function, that's this print statement running, the value of I is 11 because we added 5 to it. But after the function call, it's still 6. So this is what we mean when you say something is passed by value. Essentially, the argument I has been copied. The original variable is never messed with. So this is what is pass by value semantics. It is copying the value of the arguments into local variables. Pass by reference in C means passing a pointer to the variable instead of the variable itself. So this allows us to modify function arguments. So consider the modified boring function. So we're going to modify boring to, instead of taking an int, it's going to take an int pointer. So int pointer I. And instead of just incrementing I, it's going to dereference the pointer I, and then it's going to increment it. And then it's going to print the value of I. And instead of passing the variable itself, we're going to pass a pointer to the variable using the address of operator that we've covered before. So now let's run this. So you can see before the function, this first print statement, the value of I is 6. We pass a pointer to I, and then we dereference that pointer and increment the value stored at that location. And it retains that value outside of the function. We passed essentially the memory address of a variable. And then we looked at the memory address, or the item stored at that address, and we modified it. So this is what pass by reference is. Now let's take a slightly more complicated example, or look at a slightly more complicated example of modifying our arguments. So assume we're working in Python and we have a list of numbers. We want to count all the multiples of 5 in the list and sum them in one function call. So we can do this by returning 2 values. This is how we would do it in Python. We can return the sum and the count. So consider this definition of a Python function, oddfunc. Actually, let's just take this into the IDE as well. We don't need to analyze it here. Yeah, scratch pay y. Oh, and I still have it here, so that's good. So we can look at this function. It takes a single argument. It has 2 variables, fsum and count, and it sets them equal to 0. And then we iterate over the elements of our list. We check if it's divisible by 5, if this is equal to 0. If it is, we increment the sum. So we add that multiple of 5 to our total sum of the multiple of 5. And then we increment the count by 1. And then after we've completed this process, we return both just as a tuple, which we can assign as a tuple. So we have this list of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 15. So there's 3 total multiples of 5 in this list. There's 5, there's 10, and there's 15. So their sum is 30, and there's 3 of them. So if we go ahead and run this, then we should expect to get the output 30 and 3, because we're just printing the sum and the count here. So how could we do the same thing in C? In C, we can accomplish the same thing by passing in pointers to the fsum and count variables. So particularly, we have this function oddfunc. It has a pointer argument fsum, a pointer argument count, and then it takes an array and the length of that array. Again, we have the value at fsum equals the value at count equals 0. So the same thing as we did in Python, we're initializing these values to 0. And then we're iterating over all the elements of the list or array that was passed into us. We're checking if it's divisible by 5. So a sub I mod 5 equals 0. We are going to dereference fsum, and we're going to add a sub I to that total sum of 5. 5 sum is what fsum is short for. And then we're going to dereference the count pointer and increment it by 1. So this should give us the same output. And let's make sure it does. So back in scratch.c, let's bring in oddfunc, delete that, indents. Okay. Now we need to actually call this. So we have some work to do here. Instead of just, I mean, it really is the same process, but we can't initialize them in the same way. So we're gonna have 2 int pointers, fsum and count. Actually, we don't need to do that. We'll just initialize them as integers, pass the address, because that'll be much easier than statically allocating memory for them, messy. And then let's take the list. We can pretty easily just move this into a C declaration by just saying int L that equals, and then just change these to curly brackets and colon. We're good. Now let's call oddfunc address of fsum, address of count, our array A, and the length of A, which will be 11. And then after this, we're going to go ahead and print the value of fsum and count. So %d, new line, fsum, count. Okay. And let's go ahead and run this program. And again, we get a 30 and a 3. So the thing I want you to take away here is there's going to be times when you're writing data structures in this course, and you're going to want to do things like return multiple values from a function. When you want to do that, you should instead think about doing this, passing in pointers and modifying your arguments, modifying the pointers that you passed in. This, more often than not, you're going to be able to accomplish the same thing you would do by returning multiple arguments with this method instead. The other way to do this would be to pass in a struct or return a struct, but that's going to be a little messier, and I would not recommend doing that. Instead, just try to modify your arguments. So we've talked about this pass by reference and pass by value, but really in C, everything is pass by value. So let's see what's actually happening when you're using the pass by reference semantics, okay? Like I said, in C, everything is passed by value. So the values of pointers are memory addresses. They are just numbers. When you pass a pointer to a function, its value is still copied into a local variable. A copy of that pointer is made. The value of the pointer you passed in is copied to the local pointer variable that was created. If we modify the pointer value inside the function, notice that it doesn't change outside the function. So we can modify oddfunc to take a look at the value of the pointer inside and outside the function. And we'll just modify this here slowly. So the biggest thing is we want to change this from array indexing to just dereference. And instead of doing a sub I, we're just going to do star A. And we're going to increment A every time, A++. And every time, or maybe just after. So after we've incremented it, we're going to print value of L inside func. And we're going to print it as hexadecimal since it is a pointer. Print the value of our argument A. Remember that this plus plus notation is just equivalent to plus equals 1. So we'll actually make that just to be more clear. Does that look like about what we did? Yes, it does. Okay. And let's print its value outside as well. So before we call it value of L outside func, or before func, and after func. That's annoyingly not case sensitive. L. Okay, I think that should be what we need. Right, so we can see the value of the pointer, the base pointer L, before it's passed into the function is this 8d10. After it has been incremented, it's increased to 3c. Because again, we're assigning to this. We are permanently changing the value of this argument. But again, because it is just passed by value semantics, the value of the pointer outside of that function is not changed. It's still the same as it was originally. Okay, so this is what we mean when we say everything in C is really passed by value. Passed by reference is just passing a pointer. So you can modify the thing at that memory location, but it is still passed by value semantics. You are just passing a pointer instead. Okay, so now let's talk about pointers to structs versus structs. So now that we understand pass by reference and pass by value and what we're doing when we're passing arguments to functions, the value of what we pass is copied into a local space. It should be hopefully obvious why we would want to use pointers to structs instead of structs. A pointer, as we previously saw, the size of a pointer is always 8 bytes. It's a constant size. It never changes. When we're creating our structures and the functions that operate on them, if we pass just the struct itself to these functions, it would be copied every time we call the function. This is why we don't want to pass structs themselves to functions as much as possible. Again, a pointer is constant size. It's 8 bytes. A struct can be massive, huge, a couple megabytes, which is very large. Or consider a list that has a gigabyte of data, maybe like the dynamic array that we made previously. If we pass that to another function, that thing itself, we have doubled the space consumed. We copied that entire 1 gigabyte of data into a local variable. So this copying itself takes a massive amount of time, obviously, and you've doubled the amount of space you consumed needlessly, when what you probably needed to do was just modify your argument in some way or use some specific subset of values. This is slow because there's overhead of copying, and it's very inefficient space-wise because obviously you're doubling the amount of space consumed. So it's always preferable to pass pointers to your structures instead of the structures themselves. Okay, So let's discuss how we can use pointers to construct ad hoc items such as lists of numbers or things like instances of your struct. So consider the problem of generating a list of the first n numbers in Python. We can solve this in Python using list comprehension, assuming you're familiar with those, or just by repeatedly appending to a list and returning it. So this would be a function that does it. Nums n will give you a list of the first n numbers. And just to prove this, let's just go ahead and copy this into Python as well. So scratch and fix our indentation. And let's just print nums 100. Get the first 100 numbers. And we can see we get numbers starting at 0, ending at 99. So the first 100 numbers. Natural numbers, assuming you consider 0 to be natural. Anyways, or you could also do this with a list comprehension. So this is an example of that. Using list comprehension, L equals I for I in range n, which you can see looks very similar to the for loop because it's essentially just a compressed for loop, or just a call to nums n, like we printed in our example. So in C, we can do the same thing by using dynamic memory and returning an integer pointer. So we can do something like this. We're going to take n, the number of numbers that we want. We want the first n numbers. So then we're going to malloc enough space to a new pointer L for those n numbers. And then you're just going to iterate from I equals 0 to n and fill this list with those n numbers. Remember, this is identical to array indexing, so I'm just intentionally being a little odd here by using dereference plus pointer addition to assign. But again, this is equivalent to like L sub I. So let's just go through this first. Let's prove that this works. I'm in Python right now. And I don't have my closing brace. What happened when I copied this? This is very weird. Oh, it didn't include this inner part. That is strange. It is very odd. I'm not sure what's happening here. Okay, let's try this again. It seems to be getting all mixed up. Yeah, that's not supposed to be there. Oh well, anyways, so did this, we allocate space first, and then we iterate over, and then we return. This should be indented under the for loop, and this can be outside of it. So again, we're just allocating enough space for n numbers, and then we're iterating from 0 to n to fill this array with the n numbers. So let us actually, we can even do this with a nested call. So I have another function, print int array, that I made, just in a header file, but all it does is just print an integer array. So let's give it the return value of nums 100. So print int array takes an array and the size of the array. But anyways, so we can see again, we output 0 all the way to 99, the first 100 numbers. Okay. So what I want you to take away here is whenever you need to construct something in an arbitrary way, such as like instantiating a class or doing something like this, where you need a function that gives you like a certain collection or some subset of elements that have a certain property or something like this. Consider returning a pointer instead of anything else like a static allocation or something. You could inline this whenever you need to do something like this, or if you only need to do it for one thing, but it's not as clean. It's much cleaner to make a function that does this and just return an integer pointer. So you should absolutely use this method to create and return instances of your data structures. You should have seen this in the previous programming example, and I'm going to do it again in the next one, but constructor functions, functions that return a pointer to one of your structs. So now let's move on to C strings. Let's discuss what strings are in C and how we can work with them. In C, strings are just arrays of characters. They're a char array. We can use all the same operations on them that we use on pointers. So this is an example of us statically declaring a string S. I will paste this in and delete the rest of this because we don't need it anymore. Pull that up and indent this. So just like how we, in the same way when we do like int a array equals brackets 1, 2, 3 or something like that, we can statically declare a string in the same way, just like this, which is useful to do, but it is still just an array. So we can see we're using array indexing to pick out individual characters from this S string. We can use addition plus dereference as well. Again, it's all equivalent. And this is just a pointer. It is just another array. Okay, so if we run this, we should get this, all space separated, because we're just printing the first 4 characters, and after each one, we print a space as well. So we just get the word this. Okay, so all strings in C are terminated with a null byte, which is just a 0. In this case, when you're statically declaring something, it's implicit. So this actually has a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 characters in this sentence, but there is actually 17 characters stored in memory. The 17th is that null byte, that 0, that's created when you're implicitly doing this. Actually, just to see that, let's go for int I equals 0. Oh, no, I messed that up. I actually want to use the automatic there a little bit faster. I am being garbage right now, sorry. Okay, so int I equals 0, I less than 17, yeah, I plus plus, and we're just going to print the integer value of each one of those characters. So format it as an int, and we're going to pass s sub I. So you're going to see the 17th last character is going to be 0. Let's not do spaces, actually. I don't like doing spaces. Actually, we can just use print int array for this. Yeah, we don't need to do this. Okay, print int array s, it might complain. We'll see. 17. Type system, or it won't. Let's find out. Ah, yes, that would make sense because again, this prints in arrays, so it's going to step in a different way. Yeah, not fun. Oh well. Actually, let's just go mess with it real quick and make print char array. Nah, that's not worth it right now. Anyways, we just want to print the integer value here. And this should pretty much do what we want. Yeah, and then we'll just print a new line right here. Okay, so what you see here is just the ASCII value of all of these characters. If you look them up in the ASCII table, you would see the value of T is 116 in decimal, 104 is H, 105 I, et cetera, et cetera, et cetera, all the way to 103 G, and then this 0 here. So this 0 is that implicit null byte hidden in memory. You can certainly make invalid car arrays that don't end in 0. But as I was getting to here, any function that operates on strings in C knows where the string ends by this null byte, this 0 that's stored at the end. So if you have a string that does not have this, then the function that operates on a string, like if you're using string compare or strcopy, might just run off into empty space in memory and eventually give you a segmentation fault because it just keeps trying to copy all the information there as long as there's space in the destination array. So we can print a string by checking for this null byte as we increment the pointer. We can just use a function like this, print string, which is pretty simple. So let's just copy and paste it in real quick. Indent, so it's better looking. We don't actually need these. Only one statement, no need to guard it. But yeah, so we're passing the car array S, which again, arrays are just pointers. So we're going to check if the value that S currently points to is equal to 0, or as long as it doesn't equal 0. Then we're going to print the value at S, and then we're going to increment it. So this is the same as I believe it would be this, dereference, and then increment. So the dereference happens first, and it's passed to C. So it prints the character, then it increments the pointer to point to the next character. Okay, so well, we don't necessarily have those new line. But I suppose if we just put a new line here, then it's all good. So let's comment this out. And get rid of some of this. Let's use our print string function here on the character array S. And you can see that we do print the string. And again, we continue while S does not equal this null byte, which we could also replace this with a 0, just to make this really clear. It is just checking for a 0. Still functions the same way. We could also add parentheses here. It will still function the same way, or not. Yeah, I don't think it actually passes the value over that way. Odd. Yeah. Well, anyways, the order of operations says dereference happens first. We give it the value, and then we increment it. Okay. Now, you don't need to write a function like this, so please don't think you need to do that later. You can accomplish the same thing using normal printf. Printf has a directive for printing format strings, or printing just string literals. So this is just the same as printf %s s. Is this an error? Good old autocorrect spinning away from us. And again, we get the same thing. This is a string. If we uncomment this, we'll print it again. But let's see if we can create a string that does not have that null byte there at the end. No. Okay. So now that we understand strings are arrays. They are character arrays. Let's look at 2D arrays. So you're probably used to working with lists of strings in Python. That would be pretty easy to do. In Python, you could just have like L equal to, oops, this is, and I'll just leave it at that and then print it. Yeah, very easy to make lists of strings in Python. A little bit more complicated in C, but we can figure it out. So how could we work with arrays of strings in C? Strings in C are character arrays or character pointers. So what we need is an array of character pointers or a pointer to car pointers. Okay, that sounds a little confusing, but we're going to get into it. So we can declare an array of strings, array of car arrays like this. So this is the declaration semantics for a 2D array. This is saying I have an array of 5 character arrays, and each of those 5 character arrays is of length 5. So each of my 5 character arrays stores 5 characters. So what you actually have in memory is basically a 2D grid. So you could say this, have like A, and then a 0, B, 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 and then a 0, C, 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 0. Again, we have to have that 0 there to terminate the string. And then D, 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 0, and then E, 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 0. So that null byte is counted. When we're declaring it this way, statically, that null byte is counted as one of these characters. So we have 1, 2, 3, 4, 5. And if we were actually using, say, 0 indexing, then we have 0, 1, 2, 3, 4. This would be the index of each of these in our total array. So if we had like index data and yeah, that's how we would separate these. Okay. I'm going to work with this a little bit more before we discuss the structure of what a 2D array looks like in memory. So let's populate our array of strings with a nested for loop and print the strings. So let's just copy this into our IDE. And actually, I'm going to clean this out a bit. It's getting a little junked up. Don't need any of this anymore. Let's take our code and copy this. Okay. Let's indent this so it is not gross. So again, we have this 2D array that we're working with pretty much exactly. So we're going to iterate over the rows, so to speak, of this 2D array. And then for each of the rows, we're going to iterate over every single column. And we're going to set a character in it. In this case, it's going to be A plus I. In this way, we're going to get exactly what we have here. We're going to get a bunch of A's, and then we're going to get a bunch of B's, and we're going to get a bunch of C's. But notice in the inner loop here, we're going from 0 to less than 4, because again, that 5th placement, that index of 4 needs to be a null byte. So they are legitimate terminated strings. The outer loop, however, does go from 0 to 1 less than 5, so 0 to 4. Ranges over all rows. Okay. Again, notice like just by looking up the ASCII table, you can see like A will be like 49 or whatever. So then A plus 1 will be B, A plus 2 will be C, A plus 3 will be D, A plus 4 will be E. Yeah, alphabet. Yes, so we're just going to get a list exactly like this. Okay, enough talking. Of course, we didn't print anything, so yep, let's grab the print code. And yeah, you can see that we exactly get our string of A's, our string of B's, C's, D's, and E's. So 5 strings of 5 characters counting the null bytes, 4 without it. Zoom out a bit. It's a bit too close. Okay. So the previous 2D array is, again, it's just a pointer to pointers. Yeah, so now I think it's time to talk about this a bit more. So in the outer array, it is in fact a bunch of pointers. So we have an array here of 5 things, 0, 1, 2, 3, 4. Yeah, 4 just has a bigger box. Each of these is their own car pointer. It is just 8 bytes. It is just a number. Car star. These in turn point to other pointers, other arrays, in fact. So you have, again, an array of 5 things, which is a 0, or sorry, in this case, A, and then a 0. So this is what it looks like in memory. You're going to have 5 lists and 5 pointers that take you to those lists. And notice that this is not necessarily contiguous anymore. The arrays, these numbers, these 64-bit integers that are the pointers, they are stored contiguously in memory. But these pointers can point anywhere. These could be located anywhere in memory. They're just somewhere on the heap because they're, well, in this case, they're on the stack because you statically declared this 2D array. But we're going to build it on the heap now instead. So again, the previous thing is just a pointer to pointers, right? So it's the same as this declaration of a car pointer pointer. The initialization, if we're doing this, is a little different though. So first, we need to allocate enough space for 5 car pointers. Remember this initialization here, 5 car arrays. So we need 5 character pointers. And then we need to allocate enough space to each character pointer, each of these guys, for 5 characters. So they have all the space they need to store their 5 characters. So that's all we're doing here. We're ranging over the elements of car pointer pointer SS. And we're saying that it is equal to the return address of this malloc call, which allocates enough space for 5 characters. Okay, so let's just go ahead and grab this and play with it a bit. We're not going to go through actually populating this with characters. It's not really relevant right now. What I'm mainly trying to get at is we have to be careful when we're dealing with 2D arrays not to create memory leaks. Pointers to pointers are a little tricky. So from the previous example, if we just free SS, like if we just did free SS, then have we freed all of these ones, all of these pointers to pointers, or all of these subpointers that actually contain the list items, all of these A's? No. Free isn't recursive or intelligent. So the correct way to deallocate this 2D array is to iterate over its elements, rows, and free them first. Then you free the top level pointer. And it is essentially the reverse of this process. So first we allocate space for the top level pointer, the pointer to pointers, and then we allocated space for each pointer that SS points to. Instead, what we need to do is iterate over those pointers and free them. So we just do free SS sub I. And this way we avoid memory leaks. Okay. So just be careful that you're not doing something that's going to trip you up sometime later in your program. So hopefully you understand how function arguments are handled in C and how you can use this to your advantage to do the same things you would do in a language like Python or Java in C++, or C, not C++, sorry. No C++ here. You should also understand what strings are in C and how you might work with the collection of strings, a 2D array, the grid. You should also know how to be careful when working with nested pointer structures to avoid creating memory leaks. So we're going to go over another programming example using some of the things we've learned here. And in particular, we're just going to implement a dictionary very quickly. Thanks for watching, everyone. Thank you for your time.